going to hit record. So I am, of course, teaching this in-person version of Calculus 3, but then I'm also teaching the online asynchronous version of Calculus 3, which is where, I just post videos and folks watch them at their leisure and all this sort of stuff. And so I'm hitting record to post this video later on. Those videos are not restricted, so you also will have access to them. They'll just be in my same content folder. So if there is a day where you have to miss class for whatever reason, you can choose to watch the video online. Of course, I prefer teaching in person, and I hope that, especially you who've signed up for this class also enjoy learning in person. And so I hope that even though I will be posting the videos online, that in general, I still expect to have good attendance, and I would like you to come to class and all that sort of stuff. So we talked a little bit before class, and in general, I try to get here at least 10 minutes early and kind of answer any of your one-on-one questions and things that you may have. I'll kind of try to save all of the important questions for 150. So that way, when class formally starts, if there are any important questions, that's when I'll answer those. So one important question that got asked was kind of in the format of these lectures, and also where to find the content for this class. So I'd like to go over that now. I'm on our D2L page, which is where we will have the vast majority of our content. Sadly, we do not have a ton of time to go over like the syllabus and whatnot in today's class. So I will be getting into the math fairly soon here, but there are a couple things that I need to showcase on D2L. One of them being, so you can click on this Learn the Course Content. You can also go up here to Content, or you can go under Quick Links to Class Notes / Videos. Kind of any of those will more or less take you to the same place. And this is where all of the instructors have their folders where they will post their notes and things that they want their students to do before coming to class or have access to during class, that sort of stuff. And so I'm kind of top the list here because I have lecture 1 and lecture 4. That's how it's enumerated anyway. And so that's my last name, Ryan McCombs. A little bit of how to learn in this class. And so I've written down here like a decent order of operations, which more or less just says I have pre-class videos. You should watch those before coming to class. Otherwise, when you come to class, you may not take as much from it. And then kind of for our test 1 or unit 1 content, you can see that I have my notes. So this is a PDF document. So I recommend that you download that onto your favorite tablet or print it or what have you. But have access to that. We'll be filling out some of that here in today's class, and we will continue Wednesday and Friday and so on and so forth. And then I also have a link to the pre-class videos. So those things that I'd in general like you to do before coming to class. I understand that you may not have stumbled upon this, and so this one time here, right, you may not have seen these the pre-class videos before coming to today's class, and that's okay. I'll kind of try to take it a little bit slow through the pre-class videos before we get into the new stuff for today. So that's where you find the content that we'll be going over in class here. As is the case with all of your courses, right, please take the time to read through the syllabus. Our syllabus is very detailed, kind of has all of the if-then conditions and what happens, if you're sick for a quiz, and what happens if you have to miss recitation and all that sort of stuff. So there's a lot of that built in. And that's just because we have a very large class. There are over 1,000 students taking Calculus 3 at MSU this semester, right? And so it's important that we kind of have the rules written down, so that way we're not treating some students more favorably than other students, right? We don't want anyone to have kind of an unfair advantage. And so this is kind of our way to make sure that we are treating students fairly. So we largely do follow our syllabus. Likewise here, you may have seen under the quick links, right? So you have a link to the syllabus. You also have a link to the schedule. So if you're wondering what are we covering in class, what pre-class videos should you be watching, right? We're going to go click on the schedule. So you can see that today's class, we are covering 12.1 and 12.2, kind of some introductory topics. And then in Wednesday's class, right, we're going to cover 12.3, which means that before then, I'd like you to watch the pre-class videos for 12.3. And then we'll go over the in-class stuff. all of these numbers, right, the 12.1, 12.2, 12.3, these are all nods to our textbook, right? So in the syllabus, you'll learn that we have Stewart Calculus, 7th edition is our textbook. So when it says 12.1, that means chapter 12, section 1 of the Stewart Calculus book. The textbook is recommended, it's not required. I hope that with my pre-class videos and notes and the in-class stuff that you will have all of the definitions and theorems and whatnot that you need to succeed on our quizzes, our exams, things like that. But every once in a while, right, you've done maybe all of the homeworks and whatnot, you're studying for the exam and you want a few more problems. And that is a great thing about the textbook. It has lots and lots of problems. And so we do use an old version. It's Stewart 7th edition. I think they're on like 10th edition or something like that now. Consequently, you can buy the used version of Stewart. Well, sometimes you can find it on Google and whatnot. You may just be able to Google search and find a PDF. You may, or you can buy it on Amazon quite cheap, like a used copy or something like this. So we're not trying to break the bank with our textbook. I thought I saw a hand here somewhere. Yes, question. So I heard the first part. Will the quizzes be online and also? And this is one of the things that, so on Thursday, by the way, we have our recitation this week because we haven't covered that much content. Our recitation this week is going to be based or kind of going over the syllabus. And so kind of just an FYI, I can answer a few of these syllabus questions, but it is quite long, right? And so consequently, I won't be able to go through the entire syllabus here in our class today. But the answer is that the quizzes are online. It has one of these lockdown browser things, right? To make sure that you're not going to Wolfram Alpha or something like this, and or Google searching for the answers. And likewise, we have a couple online tests, but we do have an in-person midterm, which will be in your recitation about halfway through the semester, and we'll have an in-person final exam. So the in-person midterm is largely to prepare you for the in-person final exam. So those two will be in person. The other ones, unfortunately, we don't have an in-person option really for the quizzes and the online tests. I guess we do have a proctoring center in the math department. It's not like super large or anything like this, but it could house a few people, but you would still be taking that on. You'd probably bring your laptop there and take it, right? So I mean, kind of it would just, you would still have to take it on a computer. There's not like a printed out version. Good. Let's see here. Any other questions before I transition and we start doing some math for today? Oh, sorry, yes.
Last semester, the quiz and exams were open note. Are they going to be the same like that this semester?
So the question is, last semester, the quizzes and exams were open note. Is that the same case for this semester? No, that was a pilot. We got some negative feedback about that, first of all. I don't know how much detail. I could spend too long talking about these things, but the answer is no. And part of that is because, right, when you go and you take your midterm and your final exam, you're going to have one of these desks here. And to have an open note or open book and whatnot and try to like spread out and be able to like write down, it's just not feasible. So that's one part of that. And of course, right, we're trying to create quizzes and the tests and whatnot should prepare you for the final. So if you're kind of able to use that material some of the time, but not on the final exam, it's kind of counterintuitive. So no, that pilot, everything is going to be closed notes, closed books for our quizzes and exams and whatnot. And I'd be happy to talk to you more, or any of you, more about that and kind of the decision on why that pilot ended. So, all right, well, why don't we go ahead then? And I would like to get into the math again. So if you go to my folder and you download, under the test 1 content, we have the notes and we have the pre-class videos. So this notes is just like a PDF. And it's labeled, right, things that I'd like you to do before class. So videos before class, and then the during class stuff. So that's what we're going to be doing now. And then this is one of the few cases where I think many of you have probably experienced some physics and whatnot, have seen vectors before And so I'm not going to have time to talk about this fully in class, but I have made some videos, just basically a recording of my lesson on this, and I've put that in the playlist. So that way, it's been a little while since you've messed with vectors and vector addition and scalar multiplication and whatnot, you can refresh yourselves with those. But next time in Wednesday's class, we're going to move on to the dot product 12.3. So you should watch the pre-class video there, and then you can see what we'll be doing during class. Okay, that being said, why don't we go ahead and I will switch over to my iPad here. And largely, the way that I start most of my classes is doing a quick refresher of the pre-class videos. Again, if you didn't happen to see them this time, I'm going to take it a little bit slower than I normally would. But this is what the pre-class videos look like filled out. And here in Calculus 3, we are upgrading calculus to more dimensions. So for a long time, and I mean basically since the beginning, of your favorite algebra class, you've been dealing with two dimensions, x's and y's. And so you've learned how to do a lot of things in two dimensions, graph functions, right? And well, even in calculus, taking derivatives and integrals and all that sort of stuff, right? You've done this with rather few variables. And so largely Calculus 3 is about upgrading this to a 3 or even 4 variable calculus. And so what's kind of the headaches that are incurred when you upgrade and you have more dimensions? And so we have to kind of spend a little bit of time doing the algebra, right? Before we do the calculus of 3 dimensions, we have to do maybe the algebras and whatnot. And so in this here pre-class video, we talk about, well, yes, you have the x and the y axis, but now you also have the z axis. So when I draw these things, I put x and y on the table like this. So they're flat. Typically, x comes out of the page, y goes off to the right, and then z goes up. This is not a random ordering. It has to follow what's known as the right-hand rule. And we'll learn more about that in 12.4. But you can't put these kind of willy-nilly. And I do go into, like, if you decide you want x off to the right and y coming out of the page, then it turns out your positive z-axis has to go down. So again, these are not like random or willy-nilly things that you have to follow the right-hand rule when it comes to this. And so that's this bit here. Now, normally when you have just 2 dimensions, right, you kind of have 4 quadrants. So we talked about back in your favorite algebra class, quadrants 1, 2, 3, 4, and they go kind of counterclockwise, starting at the positive x-axis. When you upgrade this into 3 dimensions, it turns out that you have octants. You have 8 of these pieces. So you have one that's kind of sticking out, kind of maybe here. You have one behind it, one below here. And that's all the stuff where your y's are positive off to the right. And then you also need all the stuff where your y's are negative here on this other side. And so in total, you're going to have 8 of these things, and hence the word octants. Now, unlike with quadrants, there's not kind of a good enumeration. There's not kind of a meaningful way to enumerate these things. And so everyone can agree that maybe the first octant should be in the foreground where you have positive x's and y's and z's and whatnot. But beyond that, it doesn't make sense to say the second octant. There's no kind of reason why you would call one of these things 2 versus any of the others. And so hence there is a first octant, but it doesn't make any sense to say the second octant or the third octant or anything like that. And then once you have this, we get into, well, can you plot points? So in the same way that you used to play this game in 2 dimensions in your favorite algebra class or arithmetic class, right? We are now plotting points in 3 dimensions. So if I have the point 1, 2, 3, we need to go out 1 in the positive x-axis direction. So that's kind of coming off the page here. Oh, sorry, -2 for y. So for y, you would go backwards 2, so away from the positive y-axis, 2. And then you need to go up 3 in the positive z direction. So you can plot points. And one of the things that we'll talk about here in today's class is, well, once you can plot points, we plot many points, and you can plot curves and surfaces and all that sort of stuff. So we'll start talking about plotting surfaces. There's some fancy math notation here. This script R is usually stands for all real numbers. You may have seen this in an algebra class. Now that we have 3 dimensions, an x dimension, a y dimension, and a z dimension, right? There are 3 of these things, 3 real axes. And so this usually gets denoted as r cubed, the boldface R. So this just means kind of all of space. So if you see this, it just means the x can be any value, any real number, the y can be any real number, and the z can be any real number. So those 3 together will form all of space. And that's it. So that's, after that, we have vectors and whatnot, but I'll let you guys do that after class. But that's the pre-class notes in a nutshell. So again, there's a recording of this where I go over it much slower, but that's kind of what you're intended to take from the pre-class notes. And then I would like to transition here into the stuff that I intended to do during class. But before I do that, are there any questions about what I just talked about? The upgrade to 3 dimensions. Yes. So yeah, this is kind of a set notation here. And we don't do, I guess, so in 14.1, we have functions of several variables, and we have domains, right? So anytime you have a function, you maybe one of the first things you can talk about is its domain and its range. Now, those inherently are sets, right? So in this case, its range, its set of outputs are going to be z values, but its domain, its set of inputs are going to be x, y coordinate pairs. So we're going to have sets in that regard, but most of the time when I want to ask, what is the domain of this function, the answer is quite often a picture, right? So the set's kind of rather boring to write down, but we'll largely be doing that with pictures. So yes, we'll have more sets, but that comes a little bit later in chapter 14, and maybe it's not as neither of those are 3-dimensional sets. Good. Any other questions? Yeah. So the question was, a 3D function can't have more than one output for an XY coordinate pair. That is a true statement. So that is in the definition of a function, you have to have a single output for each input. So if your input is going to be an XY coordinate pair, there's only one output. And you can even upgrade that to more dimensions, right? So I could give you a point in space, right? X, Y, Z sort of deal. And maybe depending on the coordinate system, I'm talking about this point right here. And we could have a temperature function of that point. So that's actually like a 4-dimensional thing, right? Because it has an X, Y, Z input. And then there's a temperature that, we can give as an output right there. But of course, we'd have to freeze time, right? Otherwise, you would need X, Y, Z, T for time. And then maybe you could say a temperature. Right now we're talking about 5 dimensions. So it can get crazy fast. But yes, there should only be one output for each input if it's going to be a function. You have other things that aren't functions, but if you want it to be a function, you need one output. Yeah. Yeah.
I was about to say, what about a vertical surface where you have infinite z outputs for x, y, z?
Yeah, so then it's not a function. It's still an interesting set of points. And it wouldn't be a function of z anyway. Z is a function of x's and y's. But it could be a function of y in terms of x and z, for instance. So it could be a function with respect to some other variable. But there wouldn't be a single output, a single z value output for each xy input. So it's just like, kind of like a circle back in our Calc 1 days or our algebra days, right? This is a perfectly fine and interesting shape and set of points. It's the set of points, maybe if I do just the nice one, that satisfies x squared plus y squared equals 1. It just happens to not be a function, right? It doesn't pass the vertical line test. So it's not saying that we can't talk about this at all. It's not a function, right? Still, we know how to take derivatives and stuff like this with implicit differentiation. And so we still know quite a lot, and we could, talk about even the slopes and whatnot for this function. But it's just, for this curve, but it's just not a function based on that definition. All right, I feel like I'm getting a little bit sidetracked. So, but this is good. Let me go ahead and transition now into the stuff that I wanted to talk about in today's class. And so in the pre-class video, we talk a bit about plotting points. And so here I'd like to go ahead and talk about surfaces. And so the first thing is kind of, and again, this is kind of bringing back a lot of what we used to do in algebra. So I have this example: determine if the point 1, 4 is on this line, x minus 4y equals 1. One way to do this back in our algebra days, right, is, well, I could sketch these things, right? I could make a graph and I could plot the point 1, 4, and I could plot this line, right? And then I'd be able to visualize everything and I can just look, is it on there or not? So that's one certainly viable way to do this back in our algebra days. But we're going to be upgrading this into 3 dimensions. And I may not have the luxury of knowing what all of these things look like, or they may be quite time consuming in order to plot. So maybe instead of doing it the graphical way, can anyone remind me, how can I tell if this point 1, 4 is on this line, maybe using algebra rather than graphing? Yeah, do you happen to remember? Yeah, so you can just plug it in. So let's go ahead, and everywhere I see an x, I'm going to plug in a 1. And everywhere I see a y, I'm going to plug in a 4. And the question is, does this equal 1 when I plug these things in? Is this equation satisfied? Because when I graph the line, inherently what I'm doing is I'm graphing all of the points that satisfy this equation. So if it doesn't satisfy this equation, then it wouldn't be on the graph of that line. In this case, right, we have 1 minus 16. That certainly does not equal 1. It equals negative 15. All right, so the answer is no. So this point is not on that line. But now again, doing it this way with the algebra, rather than by sketching it out and whatnot, we can actually solve these sorts of problems in 3 dimensions. So for instance, determine if this point 1, 4, 2 is on this plane. So let's go ahead and spend some time. And again, everywhere I see an x, I'm going to plug in a 1. Everywhere I see a y, I'm going to plug in a 4. And everywhere I see a z, I'm going to plug in a 2. And the question is, does this equal 1? And in this case, we see the negative 16 and the positive 16 do cancel out, and I get 1 equals 1. And so the answer is yes. If I could sketch this plane, and I took the time to plot this point, we would actually see that this point is on this plane. So this is, again, the algebra, but it doesn't just work for planes. So for instance, we have this point 1, negative 3, 0. I have this complicated surface. I don't even know what this looks like. But still, we can answer the question, is it on this surface? Please take 60 seconds or so and get me an answer for this. Is that point on this crazy surface here? All right, well, I hope you got the answer no. So in this case, it ends up saying 1 is equal to negative 3, which doesn't work out. So no, even if we could graph all these things, we would see that that point is not on that surface. Okay, well now I'd like to get into another thing that is useful to be able to do, which is sketch some pictures, right? Actually be able to graph these things in 3 dimensions. And so in order to do this, again, I'm going to kind of have us remember something that we used to do in algebra maybe, and use that to kind of inform us about how to graph this now in 3 dimensions. So I'm starting off with a very nice equation, y equals 1. Now y equals 1, again, one way to think about this is that you could write it y equals 0x plus 1, right? The good old mx plus b. And you can see very quickly that this is a line. It's a line with slope 0 and intercept 1. So you can very quickly sketch this. There's 1, slope of 0. There it is. There is y equals 1. So that's certainly one way to do this in the 2-dimensional sense, because we know quite a lot of information, right, about what lines look like and stuff about slope and intercepts and whatnot. But sadly, we really don't know anything about this, in 3 dimensions. So instead of thinking about it as a line and an mx plus b, what I'd like us to think about is equations are really restrictions. So every time you have an equation, there's some restriction that you're putting on your points. In this case, the restriction is that y has to equal 1. Notice that there are no restrictions on x in this case. X could be equal to 5, it could be equal to 100, it could be equal to anything, but y has to be equal to 1. And so when you start to collect all these points, right, what if x is equal to 0? Y has to be equal to 1. What happens if x is equal to 1 and y has to be equal to 1? What happens if x is equal to -5 and y is equal to 1, right? So there's a restriction of what y has to be, but there's no restriction on what x is. X can run free, and when x runs free, it moves left and right. So it can be as small as it wants, way off to the left, and it can be as big as it wants, way off to the right. The only thing is that the height, the y value, has to be equal to 1. So all equations are restrictions. Question before I move on to the 3D version. No. All planes are surfaces, but not all surfaces are planes. So you can have, we'll do more complicated surfaces. And so for instance, basically any piece of paper, and then you can put some curvature to it. So I'll just do an easy one. I'll make kind of a parabola sort of deal in one dimension, like a taco. Right? And so this is a surface. It has some curvature to it, right? It's not a plane though, right? Planes have to be perfectly flat, just like lines have to be perfectly flat. So this would be an example of a surface here. Of course, you kind of have to imagine it goes on forever probably. But this would be an example of a surface that doesn't happen to be a plane. Good. So graphing the equation y equals 1 in now R3, so 3 dimensions, x's, y's, and z's. And I guess, sorry, let me go back here and describe this in words as best as possible. So this is a line with slope 0 and intercept of 1. I guess I'll be specific and say it's the y-intercept. But thinking about mx plus b, right? That's the important intercept. Okay, so now in 3 dimensions, if I go ahead and I was to draw my x's, my y's, and my z's, and again, usually x's go off to the left, y's go off to the right, and if you have it set up like this, you're guaranteed to have z going up. So this is kind of the standard picture here. And I'd like to think about, again, y as a restriction. Y has to equal 1. So x can be anything it wants. And when x is anything it wants, right, it's going to go kind of this left and right sort of deal, kind of out of the page. Also notice that there's no restrictions on z. Z can be anything that it wants. So z is going to go up and down here. The only restriction is that y has to be equal to 1. And so when I start to collect all of these points, right, so I could have, for instance, x equals 0 and z equals 0. So I haven't gone out of the page at all with x. I haven't gone up at all with z, but y has to be equal to 1, right? I have to go out 1 in the y direction. There's a point that satisfies this. But again, really, x could be anything it wants. It can run free here. There's no restriction on x. So really, any of these points right here would be perfectly good as well, so long as y is 1 step off of the axis here. And likewise with z. Z could be anything it wants. It can kind of run up and down. You can also do any combination of these things, right? So for instance, like the point 3, 1, -5 is going to satisfy y equals 1, right? Because again, there are no restrictions on x. X could be 3. There's no restrictions on z. Z could be equal to -5. So long as y is equal to 1, it's on this surface. And so when you start taking combinations of these things, where x is equal to 3, 1, 2, 3, and z is equal to -5, 1, 2, 3, 4, 5 down here, and again, you take kind of 1 step off in the y direction, kind of here. And when you start taking all of these combinations, I hope maybe you will agree with me that you end up getting this kind of vertical plane. Oops. Vertical plane that's just 1 step off of the xz plane. The xz plane would be where y equals 0. Y equals 1, it's just 1 step off. So again, x can be anything it wants, z can be anything it wants, but y has to be fixed at 1 in this case. Yes, question. How should you draw it? This seems reasonable to me. But you could also do it typically, just like when you're trying to create a line, you need 2 points, right? Any 2 points creates a unique line. Asterisk. For planes, you need 3 points. So if you had 3 points, you create a unique plane. So even if you had just 3 points, maybe this one here, this one here, this one up here, you could connect these together and shade that in. And that plane would be unique. Again, kind of all of these things you're imagining, they go on forever. I drew mine inside of a square, but it's not to say squares are any better than triangles, right? So I mean, if you drew those 3 points and you shaded that in, right, that would also be, again, imagine it goes on forever, but that would be perfectly fine plane. Y equals 1 is kind of, you may be saying that's a little easy, right? And so let's go ahead and upgrade here. And I'd like to talk about this graph, x squared plus y squared equals 4. And I see maybe just based on the time, I'll keep going and do this one here. So if we graph this equation, x squared plus y squared equals 4 in the xy plane, so just 2 dimensions, well, this is going to be your good old circle of radius 2 centered at the origin. Circle of radius 2 centered at origin. So that's a pretty good description of a circle. I'd like to play the same game, but now in 3 dimensions, x, y, z space, or r cubed. So again, there is a restriction. There's an equation about how x and y have to behave. And thank goodness in our calculus classes, right, we don't get imaginary numbers. So kind of we know that it's just the circle. If you were to do in the complex plane, right, it looks more complicated than this. But here we are. Now let's do this in x, y, z. X, y, z. And so again, x and y, they're related to one another. They are restricted based on this equation. Depending on what x is, y can't be anything, right? For instance, you know, if x is equal to 0, y has to be either 2 or -2. There's no way if x is equal to 0, y can be equal to 50. So they depend on one another. However, there is no z in this equation. Z is kind of out of the picture. Z can be whatever it wants, right? And this is not going to influence our equation. Z could be 100. There's no place to plug in any z's. So if I was to go ahead and think about, okay, what if z is equal to 0? Well, if z is equal to 0, I'm in this xy plane. I'm going to get another picture of this. And I get the circle of radius 2 centered at the origin. That's what happens if z is equal to 0. Now, what if z was equal to 5? So that's all the way up here. Well, if I was to think about when z is equal to 5, there's no place to plug that into my equation. But still, x squared plus y squared has to equal 4. They're still bound together by this equation. There's this restriction. And so they still need to satisfy that they're on this circle. Now this circle is up at a height of 5, right? Z is 5. But again, there's no place to plug that into my equation. Likewise, if z was -32 or whatnot, way down here, still there's a restriction based on x's and y's. These things are related to one another, but there's nothing about z's. And so what you end up getting is this nice circular cylinder. So again, z can be whatever it wants, but x's and y's, they have to be on this circle, no matter what the height is. So x and y have a restriction, z does not. And so you kind of get this running free in the z direction. Yes? One more time? Yes, yep. So we're not talking about here the cylinder along with its insides. We're talking about the surface itself. And so the surface itself, right, again, it doesn't have any insides whatsoever. It's just it's equal to 4. If you said x squared plus y squared is less than or equal to 4, right, now you're talking about the solid, right? Because the less than or equal to 4 gives you not only the surface, but all of its insides. But when you say it's just equal to 4, yes, you're talking about the surface itself, not its insides. Good question. All right. In the interest of time, let me go ahead and skip this one for a second. If there's time, I'll come back to it. And FYI, kind of any of the problems that we don't have time to cover in class, I will go ahead and upload those to D2L as well. So you get the video that I'll upload, and as well the problems that if we don't have time for them. So, but I want to talk about a very specific type of surface now, and that is spheres. So again, I'm going to try to kind of use what we know from our two-dimensional algebra classes and kind of upgrade this into kind of some three-dimensional stuff. And so typically when you talk about circles for the first time, these are things that are a fixed distance from a point. So all the things, again, kind of if you say a circle of radius 2, they're a distance of 2 from that center. So it's the set of points that's a fixed distance from that. So you need to know something about distance. So in 2 dimensions, right, you usually come up with this distance formula. And same thing here, we need to come up with a distance formula, but now in 3 dimensions. So the distance is usually denoted with these kind of absolute values, or the magnitude, about 2 points. So there needs to be 2 points. These points are going to be in space rather than in 2 dimensions, right? So they have x's and y's and z's. Now, if you wanted your distance formula for 2 dimensions, you probably remember, it looks something like x2 minus x1 quantity squared plus y2 minus y1 quantity squared, all inside of a square root. That's the 2-dimensional distance formula. You get this by doing the Pythagorean theorem. It's just kind of you take those differences between those x's and those y's, and then you have the whole a squared plus b squared equals c squared. That's where this formula comes from. And so consequently, if you want a 3-dimensional distance formula, the only thing that you really need to do is sprinkle in some z's. So it's very forgiving, it's very nice. You just sprinkle in those z's, z2 minus z1 quantity squared, you add that on. In order to prove that this is the right distance formula, it turns out you need to use the Pythagorean theorem 3 times. But okay, fair enough. So you need to use the Pythagorean theorem if you want to prove that this works out and gives you the true distance. But we're going to maybe use this to actually calculate out a distance. So why don't we do this one together here? My first point, I'm going to call this x1, y1, z1, since it's the first point on the list. Second point on the list, x2, y2, z2. So they have an x, a y, and a z coordinate. And if I wanted the distance, we could do the square root of 3 minus 1 quantity squared, negative 1 minus 2 quantity squared, and 0 minus 3 quantity squared. Add those together, throw them inside of a square root. And so let's see, 2 squared would be 4, negative 3 squared is going to be 9, and negative 3 squared is also 9. And so the answer in this case is that the distance between those 2 points is going to be the square root of 22. Now, a question for you is, I decided that the first point here would be my x1, y1, z1. And I chose that the second point on this list would be x2, y2, z2. What if you made the opposite choice? What if you decided, for whatever reason, you saw that first one and you said, okay, I'm going to do x2, y2, z2. And the second one, you called that x1, y1, z1. How does that influence our answer? Yeah, great. It would give you the same answer. Yes, absolutely. Your orderings would be switched, right? Instead of me having 3 minus 1 is 2 squared, you would have 1 minus 3 is negative 2. But when you square negative 2, you still get 4, right? And likewise, you would have the opposite order here. You would have negative 2 minus, negative 2 minus 1 here. And that would give you positive 3. 2 minus negative 1 would be positive 3. Square that, you would still get 9. Right? So even though the orderings would be different and you may have different intermediate steps, we would all still have the same final answer. So that's kind of a nice comforting thing. Well, now that you have distance, we can talk about a sphere. In 2 dimensions, it was circle. Now it's going to be sphere. So 3-dimensional distance, we can define the set of all points equidistant from a center point, aka a sphere. An equation of a sphere with a specific center and a specific radius. So we have the center is HKL, and our radius is R. So if you were doing an equation of a circle in 2 dimensions, it looks like this. X minus h quantity squared, y minus k quantity squared equals r squared. That is the 2-dimensional equation for a circle in standard form. So if you have the center, hk, and you have the radius, this is the equation for that circle. So if you want a sphere, well, we're just going to sprinkle in some z's. So we're going to have our z minus l quantity squared here. And it turns out, again, using that distance formula, this would be the correct formula for a sphere. All right. Sorry, yes, question. So it is still r squared. It's not r cubed. And it's the same reason that this is not a cube root here. If this was a cube root, you're absolutely right. It would have to be r cubed. But since it's still just a square root, and again, this is kind of coming from the Pythagorean theorem, that it's still just a squared plus b squared equals c squared, right? You still just have square roots, luckily. So, but that's a good point. That's another reasonable way to upgrade this, but still just squareds, it turns out. All right, so there's a couple of reasonable questions I think you can be asked. So here's a quick one. Maybe I'll give you 30 seconds, 60 seconds. Get as far as you can on this one. But find an equation for a sphere with a specified radius and a specified center. All right, so this is a pretty fast application of our sphere definition here. Just plugging in the points for HKL, right? So x minus 1, y minus a negative 2 becomes y plus 2, and z minus 3 there. Those all get squared, and then on the other side is equal to 2 squared, aka 4. FYI, right, when it says find an equation, right, this is a perfectly good equation. This is a good place to stop. Certainly, you could try expanding it out and combining like terms and all that sort of stuff. But of course, if you make a mistake, right, you could get some points taken off on a quiz or an exam or something like this. This is far safer to stop right here. Also, it's a lot easier to grade this than if you expand it all out, right? Because this right here, I can quickly see the point and the center right there in the equation. If you start expanding it all out and combining like terms, it's a lot harder to grade, it turns out. So as soon as you have an equation, that's a good place to stop. Now, another reasonable type of question that one can get asked is the flip of this, right? Rather than here's a point for the center, here's a radius, give me the equation, we could go the opposite way, right? So here's an equation, tell me what is the center and what is the radius. Now, okay, I've asked this kind of in a slightly different format, you know, kind of pretending before this that you didn't maybe know, and we had some questions like this before, describe the surface. But we can see that this is of the form, and you could write this as x minus 0 quantity squared, y minus 0 quantity squared, z minus 0 quantity squared is equal to 1 squared. And so this is indeed a sphere with radius 1, centered at the origin. 0, 0, 0. Just like in algebra days, there's a unit circle, x squared plus y squared equals 1. This right here you could call the unit sphere. It's the sphere centered at 0, 0, 0 with a radius of 1. This is an easy version of this question. The full strength version of this question, kind of the hardest thing here, would be this problem. Describe this surface in words as best as possible. So obviously this question is in the subsection that's all about spheres. You're probably looking at this, and if you're a betting person, you would say, well, it's probably a sphere, right? But still, we know what spheres, right? If we can get them to look like x minus some quantity squared, y minus some quantity squared, z minus some quantity squared, and a constant on the other side, right? Then we can say for certain that it is a sphere, and better yet, right, we're trying to describe it in words as best as possible. That would probably include, well, what is the sphere's radius and what is the sphere's center? So we would like to be able to transform what we have here into this thing with a bunch of perfect squares, right? X minus h quantity squared, y minus k quantity squared, z minus l quantity squared, blah, blah, blah. Anyone remember, there's an old algebra technique that you can convert stuff like this into perfect squares. Anyone remember what it is? Maybe someone I haven't called on yet. Here. That's absolutely correct. Completing the square. So completing the square back from the old algebra days. So we need to complete the square. And it looks like we need to do it rather 3 times, right? One for the x's, one for the y's, one for the z's. Well, it turns out, right, the y's here, there's no linear piece of y. You could write this as y minus 0 quantity squared. So the y here is already a perfect square. But these other ones, the x's and the z's, those ones need to be completed. So the way that you do completing the square is that you look at the coefficient of the linear piece. So in this case, we have a negative 2x. The coefficient there would be the negative 2. And if you take that negative 2, and again, this is the old algebra technique here, you have to divide that by 2 and you have to square it. It turns out that's the right thing to add in order to complete the square. So in this case, negative 2 divided by 2 would be negative 1. And when I square that, that would be, well, negative 1 squared is 1. So I would like to write this as x squared minus 2x plus 1. My claim is that that is a good job, that we've actually done something productive, and this is now a perfect square. But we also need to make sure that the z's are a perfect square, right? So again, the coefficient in front of the linear z term is 4. So we're going to play that same game, 4 divided by 2, and we're going to square that. And it turns out this is supposedly the right thing to add on in order to make a perfect square. So 4 divided by 2 would be 2. If I was to square that, 2 squared would be 4. So I'd like to write this as z squared plus 4z plus 4. Now, I have added a 1 to my left-hand side, and I have added a 4 to my left-hand side. In order to not ruin my equations, I need to do the same thing on the right-hand side. Otherwise, I've ruined the equation, right? It's no longer equals because I've started adding things to one side and I didn't do it to the other side. So there was a equals 4 on the right. I need to add the 1 and I need to add that extra 4 in order to keep this all equals. All right, now it just comes down to factoring. If you factor this, right, again, go back to the algebra days, it takes a little bit of time. Right, to get those motors running again, but you're going to get that this factors to x minus 1 times x minus 1. This is a perfect square, right? Another way to write that would be x minus 1 quantity squared. It's the same thing multiplied by itself. And likewise, we already had, you can write this as y minus 0 quantity squared. And if you try to factor the z stuff, right, spend a little bit of time factoring that, you're going to get that this is z plus 2 times z plus 2. Or another way to write that is z plus 2 quantity squared. It is a perfect square. And on that right-hand side, you're going to have, well, 4 plus 1 plus 4 should be 9. So now you're confident, right? You have this in the sphere equation. So you can certainly say now that it is a sphere. And better yet, to be, as specific as possible, this is a sphere of radius 3 with center of 1, 0, -2. So again, remember in the equation for a sphere, there's minuses. So it's y minus 1. So 1 is the h. Y minus 0. 0 is the k. And then the L, right, it needs to be z minus something. So it's got to be z minus -2. That's how you would get the +2 there. So that's why the L here is -2 instead of +2. All right, well, pretty good. Like I mentioned, I have written here, right, there was one problem that we didn't get to in today's class. I will go ahead and write out the solution for this and post it on D2L along with the video. The videos will be in the same folder and everything as my pre-class notes and the videos and whatnot. So just that same folder there, everything for the Unit 1, Test 1 will be right there. So, all right, I'll stick around if there are any one-on-one questions. Otherwise, have a great day, and I'll see you guys Wednesday.